All right, everyone. Thank you very much for joining today's webinar. Thank you for taking the time out of your day, also from your busy schedules to join us. Today's topic of discussion is FE test correlation with FEMtools, with a case study from the space industry. My name is Kelvin Boadi. I'm a technical consultant at Insuma Innovation. And today I'm joined here by Eddie Dascott, CEO and owner of Dynamic Design Solution, the provider of the FEMtool software. And also Naima Gearens, the Marketing Enablement Manager at Insuma, and also the moderator of today's session. So before we start, just a quick note. If you have any questions or suggestions, please feel free to use the panel on the right. And then we'll try to save some minutes at the end of the webinar to answer the questions. Experience learns that it's never the case, but in case we are able to spare some time, we will try to answer the questions. If not, then we will reach out to you personally by mail with an answer to your question. So here we have a general overview of today's talk. So we will start with some basic introduction. So some basic terminology about the validation process, so modal validation process. And then we'll talk about correlation analysis. So the toolbox actually within FEMtools and what you can find within that toolbox. So especially spatial correlation, degree of freedom pairing, mode shape pairing. And then we'll end the talk with a demo using the P200 STM satellite. And then, of course, there'll be a summary as well. So just a quick introduction. As I mentioned earlier, I'm from Insuma Innovation. So Insuma Innovation is the exclusive business partner of Hexagon in the Benelux. So for those of you who are maybe not familiar with Hexagon, and for those of you who are more familiar with, or in the world of FE, maybe you are used to the names like MSc Nastran, MSc Mark, MSc Adams. Those are all tools within the simulation suite of Hexagon. But we also have additional tools, especially in acoustics, for instance, where we have a state-of-the-art tool known as Actran. We also have a very comprehensive tools within the virtual manufacturing world as well as simulation process management, also systems and control, and so on and so forth. So with that being said, I will hand over the floor to Eddie Dascott to give a brief introduction about Dynamic Design Solution and FEMtools. So Eddie?
Yes, hello everyone. So Dynamic Design Solutions is a CE software company located in Leuven, Belgium. And we have been specializing over the past 30 years on structural dynamics and mainly integration of FEA with testing, which is mainly done in the modal domain to validate and update finite element models. So this resulted in a FEMtools software package, which is going to be used today for the demonstration part. With key functionalities is that it's a multifunctional cross-platform and solver-independent software, which means it runs on Windows, Linux. It works with the main FE software like Nastran, ANSYS, Abacus, OptiStruct, and so on. And this allows it to be used in combination with those software to validate and update FE models using test data. Yeah, so it is a multifunctional software, as you can see. The different modules are shown there, but okay, we'll talk more later about those later. And it's also scriptable, so it is also entirely programmable, extensible, which is also one of the features that we've used in this for this demo case that Kelvin will be presenting. Okay.
Yes, thanks a lot, Eddie. So with that being said, we would like to start off by giving a brief introduction into some terminologies. So here I would like to describe the validation and updating process specific to modal validation. So here correlation is it's a very vital part of modal validation. And with validation, what we mean is the process of determining the degree to which the model is an accurate representation of the real world from the perspective of the intended use of the model. So when we look at the general validation and updating process, we have on the left-hand side here, we have our analytical method or the FE model, which typically comprises of nodes, elements, from which we can then compute our eigen solution, where we basically assemble our mass and stiffness matrices, from which we can then derive our analytical or FE natural frequencies and mode shapes and other parameters as well. And then on the right-hand side, you have the experimental model or the test model, which comprises of a prototype of a text structure. This could be a derivative of a FEM model. And from there, we perform experimental modal analysis, where we excite the structure, for instance, with the use of a hammer or with the use of a shaker. And then from there, we can do all types of model extraction as well. So we can have accelerometers as well to measure the accelerance, or for instance, of the model. And then we also derive the natural frequencies, mode shapes, and other parameters as well, specific for the test model in this case. And then in the middle, you also have tools such as the modal pretest planning, which is also a vital tool between these two processes that I described. So the modal pretest planning can be used, for instance, to make informed decisions for building your test model. So for instance, how to excite your structure, where to place your sensors, and how to support your structure, and so on and so forth. So to basically close the loop between the FE model and the test model, we have the correlation analysis highlighted by the blue dotted lines below. And with correlation analysis, we are trying to basically quantify the level of agreement between the simulated and the measured responses. So the main goal of correlation here is to quantify the offsets between the FEM and the test responses. And we do that through the three main steps. So we start by first pairing the nodes and the points, also known as spatial correlation. And then from there, we also pair the numerical and experimental degrees of freedom, or the FE and the test degrees of freedom. And then we can also pair the numerical and experimental modes, also known as the shape correlation. So the results we get from that is, for instance, mode shape pairs, frequency offsets, mode shape correlation, which is sometimes represented by the plot on the left-hand figure here, right here, which is a map plot. Which basically tells us how the modes, or how each mode is in agreement from the test to the FE model here. So with that, we can also talk about spatial correlation. So when we work with two models in the same coordinate system, it's possible that some grid points sometimes might overlap or lie very close to each other within a set of tolerance. So the process of checking how many points match like this is what we typically describe as spatial correlation. So to see if two models actually line up, we can display them superimposed, like we've done in the figures displayed here. So if the coordinates don't match, then for instance, within FEMtools, we have specific transform tools where we can use to basically bring those two models together. So the outcome of spatial correlation in FEMtools is a table that shows the pairs of the FE nodes and test points. So this table is shown in the figure below, so as shown, which basically shows the pairs of the FE nodes and test nodes that are closest to each other within tolerance. And there are multiple ways of doing this. So we have, for instance, sequential pairing, which match the nodes and points in the order in which they are stored in the database. They are stored in the database. We also have forced pairing and also automatic pairing. All these are available within FEMtools. But sometimes it's very difficult to do spatial correlation because in most cases, the analytical model or the FE model has more degrees of freedom compared to the test model. But that is not the end of the story, at least not in FEMtools for us, because we can do things like mode shape truncation, where we basically eliminate data from the FE model, which does not have a counterpart in the test model. Or we can also do mode shape expansion, which is a technique to add modal displacements in the test model for the degrees of freedom that are not measured. And closely related to what I just described is the degree of freedom pair table. So the degree of freedom pair table basically connects the degrees of freedom in the FE model with those in the test database. So this table can also be created either manually or automatically within FEMtools. We will have a look at how that is done later on in the demo case. So we have to remember that mode shapes are giving us vector quantities, so they can be measured in either X, Y, or Z direction. So it's important to identify which direction these modes are basically measured in, so that we compare them correctly with the FE degrees of freedom. And from that, we can also get a result as shown below, which is a table giving us which degrees of freedom are being are associated with each pair. So each pair from the FE node and the test points, and in which direction they are measured in, basically. So once we have the degree of freedom pair table, we can start computing the mode shape parents using correlation metrics such as the MAC, which stands for the modal assurance criteria. We can also use other methods such as eigenvector orthogonality or cross orthogonality, as others might recognize. So using the diagram, we can see that the first experimental mode corresponds to the first FE mode. The second also corresponds. The third FE mode, however, does not correspond to the fourth mode. So this is not just a nice plot to have, but it helps us to basically correlate the frequencies, because you will have to, in this case, compare the fourth experimental frequency or the test frequency with the third FE frequency in order to make the right assessment of the data, because sometimes, during the test phase, modes can sometimes be switched. This helps us to also validate the quality of the test data that we are receiving, as in this case. Other correlation methods also exist within FEMtools. So for instance, we have the local mode shape correlation, where instead of looking at the full mode shape, we can look at a certain area or 1 degrees of freedom in our structure, and also compare the data in the full frequency range and identify regions in the structure where there is good correlation and where there is less good correlation, I would say. So in this slide, in the top figure, we have an example of a local correlation using the MAC contribution analysis, which helps us to identify the degrees of freedom that have a big impact on the overall MAC matrix. And what we see here in this example is a correlation that is initially very low, and by eliminating 2 degrees of freedom, we end up with a very high correlation, which is represented by the middle and the right figure here for the MAC distribution. Aside from that, we also have FRF correlation, where we compare directly the FRFs computed from our FE model with the FRFs that we derive from our test model. And then we can see whether they are in agreement with each other. So whether they have low correlation or high correlation when those two curves are close to each other. We also have operational deflection shape correlation, where we can do all types of stuff such as shape correlation, amplitude correlation, and phase correlation. But that is a bit outside the scope of today's talk, so not comment further on it. So with that being said, I would like to start an introduction into today's study case. So before I do that, I would like, on behalf of the Insuma team, say a big thank you to Redwire Space for submitting us with this model and also all the necessary data to basically prepare this session or this talk today. So the model that we are using today is the P200 STM satellite. So STM stands for the structural thermal model. And just a little bit of a background. So it's an evolution of the Proba micro satellite platform, which has extensive flight heritage with more than 25 years in orbit without any failure or on any of the launch satellites. And some specifications. So the P200 is capable of supporting payloads up to 70 kilograms and target spacecraft mass less than 200 kilograms, making it compatible with typical shared launch opportunities and small satellite launches here. So the P200 STM satellite was first tested in Toulouse in March 2019 and was manufactured by Kinetic Space, which is now known as Redwire Space. So below we have a figure of the actual satellite. And here we have the FEU model or the FEM model of the P200 STM satellites, which basically consists of panels modeled with shell elements. In the middle, we have a connection of the tank to the base, modeled with RBEs. And the tank itself here is, I don't know if it's possible to see, but it is modeled by a lumped mass, basically, to represent the tank. And on the right-hand side, we also have the point masses to represent accelerometers. And then we have hinges, the top platform, the bottom board modeled with 3D solid elements as well. And then here we also have the payload. So with the FEM model, we have two kinds of the FEM model or two models generated. So we have the one with a rigid payload and one with a flexible payload. But for today's case study, we are only considering the flexible payload for the correlation activity. And before we start doing any type of correlation, we first start with some pretest activities by computing the modal effective mass, because this helps us to understand how much mass of the total mass is contributing to a particular mode. Because here we have to remember that in general, we don't really know how much a mode is going to contribute to the overall response until we apply the loads to the structure, because things like the frequency content of the loads, the direction of the loads can all have an effect. But before we do that, the easy way or a way in which we can actually see how much each mass is contributing is by using the effective mass here to have some insights into what modes are important for our analysis. And then the next step, and also the final step in the pretest activity, is to compute the automac to check if the sensor selection is capable of identifying all the modes of the satellites. And from the automac plot that we see on this top left figure right here, we can see that most of the modes are independent of each other because they are all aligned diagonally with high values. However, we see that there are two very high off diagonal bars standing, very distinct. And in here we can identify that this is due to the fact that the test measuring sensors having insufficient degrees of freedom. So if we have a look here at the circled panel, so this fixed panel here, we can see that we are missing direction in the Z. We are missing measurements in the Z direction. And if you look on the right-hand side, we are missing degrees of freedom in the Y direction. So this is very important. And this, once again, stresses the importance of doing these pretest analysis to basically have a critical view of the test data that we receive. So this missing degrees of freedom from the test model introduces or induces a bending and torsion mode, which is then represented by the off-diagonal values that we see in our MAC plots. The good news is that in this case, the modes are 60 and 180 Hertz, so very far apart from each other with the modal effective mass less than 1%. So we can basically neglect them in this case. because in the previous slides, we already discussed that we are taking modes with a modal effective mass higher than 3% in this case. So now we can take a slight pivot and start having a look into our test data. So here we create the test model, basically from the FE model, and with FEMtools command here provided. So using the FEMtool command, this model is then converted to a universal file test model using data sets as listed here. And then we can then the UF test model is then used for the modal parameter extraction. So here we have like a wireframe, I would say, or a skeleton version of the satellite, where we have our solar panels, we have the side panels, we also have the tank assembly, the payloads, and etc. Now, it's not always the case that you might have FRFs from test data, which are traditional. So you have the output divided by the input. In some instances, you might have FRFs given to you in the form of spectra, as in the case of this of what we have here for this demo case. And this is where the FEMtools scripted capabilities comes in clutch, I would say, because using the FEMtools script, we can basically go through a couple of steps. So divide all the response spectra by a reference spectra, so A over A at the base, and then replace the response label by an FE node and degrees of freedom as well. And then check the acceleration spectra units, resample, and then trim the spectra to between 25 and 200 hertz here. So here an example is given of how that is done. So here we have a response label here, and then we basically replace that with an FE node as listed on the right image here. That is basically how we are able to overcome this. So now we can also then focus more on the test data by also looking at how we use the modal parameter extractor, which is a tool within FEMtools to curve fit FRs and extract the modal parameters. The mode shapes, the frequencies, modal damping, etc. And within FEMtools, we have two main methods of doing that. So we have the global methods, or the global polyreference method, also known as the BLSCF method. And then we also have the local method known as the Dapson method. And these work with classic output over input FRs or accelerants, so A over A, as we have in this demo case. And FRs also using different references can be combined. For this project, or for this demo case, we use 3 references and 48 responses, basically. And extraction settings via an interactive panel, which will then be shown later on during the demo case. Or we can also automate using command language as well. So here we have our reference FRs in the 3 degrees of freedom. So in the X direction, in the Y direction. So these are FRs that we derive from the shaker in the all 3 respective directions, so X, Y, and in the Z direction. So for this particular case, we use the global method. So because it has an advantage that it produces clear stabilization charts, which enables for automatic identification of stable poles. This is not to say that the local method doesn't have its own use. It also has its own use, specifically to extract modal parameters from tested data that is affected by mass loading. But in this case, the global polyreference extraction method often find a pair of stable poles near the resonance instead of a single pole. And this is due to the shift in resonance frequencies from one FRF to another because of mass loading by accelerometer sensors. But for our application today, we use the global method because it works nice and we are able to extract stable poles using this method. And we have also several methods, or we have several references available. So the LSFD doesn't just look at one, it considers all the FRs across the entire frequency range, which means it takes into account every input participation factor and even the lower and upper residuals for each reference to extract the modal displacement here. What's important here is that the LSFD it doesn't pick just one reference based on how dominant it seems. Instead, it combines information from all references at once, because one reference might be strong for some modes, but not for the others. And this approach gives a much better and complete, reliable modal extraction. And then the validation is done using quality criteria such as the MPCs, which stands for modal phase collinearity, which is an indicator to check the degree of complexity of the mode. Or we also use we can also use MPD here, which stands for mean phase deviation, which also checks the complexity of the mode, but in a different form by expressing the scatter of phase for each mode shape. And then the automated process in this case takes only a few seconds, and then we have everything that we basically need to further do our correlation activities. So here, as I mentioned, the local method also has its own use. For instance, it can be used to double check the global extraction results. So basically used as an alternative, or known as the manual method. Usually not that easy compared to the global method, but it is available in any case. And it's mostly used with challenging data, so data where we have a lot of noise or mass loaded data, as described before. So from there, we can basically extract our mode shapes, not very visible here, but hopefully become clear during the demo. But here we can basically derive all the mode shapes from the test data as well. So for the modal correlation analysis, we basically follow these steps. So we start with the modal mapping, the node point and degree of freedom pairing, and then the modal correlation criteria. So we use the MAC, or the orthogonal, the eigenvector orthogonality, and then we do some mode shape pairing and so on. So with that being said, I would like to basically switch to the FEMtools session. Hopefully everyone can still see my screen. So here we have the FEMtools GUI, or the graphical user interface. I've already loaded in the model, and I've already done some computation. So I've already computed my modes and also my modal effective masses, and also imported my element, my stiffness matrices. And all of this is done using the script because it takes a lot of time to do it, and to save a little bit of time, I decided to basically have all of that ready here as well. And here you can have an example of such a script here. So this script, for instance, is used to compute the effective mass. So as you can see, the input or the syntax is not very difficult. So here we give a command to input the FEM format, so which is an Astran, it could be an Astran BDF, or in this case, a .dat file. And then we search for the modes in the fort.f1 file, which basically gives FEMtools instruction on which ranges, for instance, from which frequency range to search for, and so on and so forth. And we can also search for the mass format using the Navstrand file, which is the fort.92 as well. We can, everything that I've described also with the script, we can also do directly from the GUI as well. So for instance, if I want to compute the modes, I click on tools, and then if I go into the modes analysis, here I can select which solver I want to use. I can either use the FEMtool solver, I can use the Nastran, I can use Ansys, Abacus, and so on and so forth. So I have a couple options here that I can choose. And then I can select the number of modes that I want to basically compute, and then the frequency ranges that I want to compute. And then below you also have your modal extraction method. So either the Lanchos or the modal Hessenberg method as well. And then if I click on OK, then it will start the computation. I'm not going to do that because it takes quite some time to do that. But in this case as well, it's good to mention that we use Nastran here. So FEMtools can basically directly interface with Nastran to basically compute the modes. And this is typically done when we have elements with, with very complex behavior in this case. So all of that is computed. So here I can, if I go here, I can view all my modes. So I have modes up to 23, and I can also animate them if I wish. So if I click on the animation tab, I can animate each of the modes. So I can go through them randomly, just pick a random mode, and then basically examine the mode shape behavior here. And then here below, I also have my modal effective mass fractions also computed, and everything is also available here inside the graphics tab, so I can also view them as well. So with that being said, I will maybe like to switch to the test model, and how I do that is by clicking on the add-ons and then going into the modal parameter extraction tab. So this brings me into a new or a different tab. And here I can basically import my test model. So the test model is already prepared in this case. So I click on the test mode for the flex payload, and then I say open. So I have it opened here. I can also import my test FRFs. So I click on this, and then I have my FRFs, which have already been prepared. And here I have my overview for the modal parameter extraction. So I can decide to show this animation in solid view as well if I want. And I can go through each and every one of these as well, and basically examine the view. And also the FRFs are shown here as well. So here we have the reference, and as you can notice from the first three, we can see we have here a straight line, and that's because we are using accelerants over accelerants FRFs. So here in this case, we are basically dividing the FRF by the reference. So we end up with A over A resulting in 1, which is why we have a straight line here. Unfortunately, the way FEMtools basically sorts this out is so that's why we have these as first. But I can decide to include them or not include them. In this case, it's not really necessary to include them, so I just decide to uncheck these first three as well. So yeah, here once I'm done, I can move on to the post extraction tab. And here I can do my modal extraction. So here I have extra settings available, such as maximum order, which is the maximum, so the order of the polynomial used basically for the extraction. I can also set my minimum frequency. So let's say here I choose 5, for instance, and then my maximum frequency, say 200. And as I select that, it automatically adjusts the maximum order for the extraction, or for finding stable poles, I should say here. So in this case, I'll use 40 here, and then I'll say here from 5 to 200, and then it basically already adjusts the graph for me. And if I click on the extract poles, it basically extracts everything for me in seconds. So here I have all my poles available, and I also have extra settings which can be used as criteria for finding stable poles. These are advanced settings that I can use, such as minimum damping ratio and maximum damping ratio, and so on and so forth as well. And here in the chart, how we basically view it is, we use these color plots to basically identify. So we have the gray, which identifies the first pole appearances. We have here the light blue, I think, for the pole frequencies stable. So to identify the frequency pole that is stable, and then and so on and so forth. Here we also have this color right here, signifying the frequency and damping stable, and so on and so forth. So once I have that, I can click on store pose to store them. So it basically does everything for me automatically. So I'm using the global method here. So everything is automatic. And then I store the pose. So once I store the pose, I can then move into the modes extraction tab, where I have all my modes identified here. And if I go here below, I can click on extract modes and then basically extract all the modes that I am interested in. And with that being done, it automatically creates some automatic plots to tell us if the modes are independent of each other. So as we can see here, we have very nice, all the modes are in the diagonal with very high mark values. We have some off diagonals, but they are pretty low. Typically, you aim for around 25% off diagonal values, but this also depends on the industry that you are in. But in this case, we have a very good automatic plots showing that the modes are very much independent of each other here. Once we have that, we can also say extract the modes as we've already done, or we can also reject the modes if we are not satisfied, and maybe find or use other settings to get different stable poles in the previous tab as well. So once I've done everything, FEMtools automatically saves this into my database. So if I click on the exits here, I should have everything available. So here I have my test mesh now available to me with all the frequencies also available. So I can also animate them as well in this tab as well. A bit flipped over. So with that, we basically now have all the test modes now. So and also the FE mode. So we can go ahead with the correlation as we described. So if I go into the test into tools here, I'll have to first mention that I have to switch now into the correlation tab because I was working in the model updating. And then if I click on tools, I have tools available now. So for instance, I can do my node point pairs. So if I click on it, I'll be using the automatic methods and I'm pairing all the nodes with all the test points. And I can also set a maximum distance, but it already provides me with a value. And if I click on OK, then FEMtools automatically does that for me. So I have here my test points overlaid onto my FEM nodes here, showcased by the different colors here. I can also have it in a tabular form. So if I switch to the table tab, and if I go into correlation, so FE test, I can click on the node point pairs, and then I have all the node point pairs and the distances between them and the offsets as well, if that is the preference as well. So with that, I can also move directly into the degree of freedom pairs here. So if I click on the degree of freedom pairs here, I also have additional settings here that I can set. Here I'm using the translations degrees of freedom here. And then if I click on OK, FEMtools computes that for me as well. So as I can see here, giving me a very nice visual, and then also gives it in a tabular form here for the degree of freedom pairs to see which degrees of freedoms are identified for each pair and in which direction they are measured in as well. And so once we have the degrees of freedom pairs, we can then also compute the mode shape pairs here. So if I click on the mode shape pairs here, here I'm also using the automatic method. So if you can notice, as you can notice, everything that I'm doing or most of the stuff that I'm doing is done automatically within FEMtools. Obviously, you have the option to do a manual pair as well. But in this case, FEMtools does a great job already with the automatic method. So yeah, I can, for instance, set the minimum mark percentage. In this case, it's set to 60. I'll maybe change it to 40% here. So that's the minimum mark value that I expect. And here I am basically pairing all the modes, so all the FE modes, and with all the test modes here. And the parent metric that I'm using here by default is the modal assurance criteria. So I can click on OK, and then I get it computed for me here. So here, if I click on this, I can see the mark pairs. So for the first pair, for instance, 98%, which is pretty high, good. And I can also animate it as well to basically see how the test and the FE model basically deforms, which is good for visual representation or for visual checks. So here we have 7 pairs identified based on the settings that we chose. Of course, we can increase the minimum mark value or reduce it. It's based on you as a user to determine which one is appropriate. But here we've identified 7 pairs, which is good enough to continue with our mark or to continue with our correlation. And once we do that, it automatically also calculates or gives us a modal assurance criteria plot here. So if I click on it, it shows it here, comparing the test modes with the FE modes here, as you can see here. Another metric that we can also use here, obviously here we are using the Mac, but we can also use the eigen vector orthogonality or the cross orthogonality here. It takes quite some time, so I have it already loaded in here to showcase the differences. So between the two, this method basically does or uses the Gaussian reduction, so it's sometimes can take a couple minutes to finish, so which is why I'm not doing it live. But I have it already computed here, and I can already see some that I have very high modes now for mode 5 and 6, which are the local tank modes. So maybe if I go back into this view and if I go into my test model here, and if I view my modes for mode 5 and 6, I see there is a local mode here for the tank here. So for mode 5 and 6. And with the modal assurance criterion, it assumes uniform mass distribution. But the EVO, on the other hand, does not assume mass distribution because we have, if you remember from the FE model that I showed, the tank model or the tank is modeled as a lumped mass. So we have a concentrated mass in the middle of the satellites. So this right here, the EVO, does a good job showcasing this local mode. So we get a very good correlation here. Or a better correlation compared to the Mac. The Mac also gives a good correlation, about 60%, if I'm not mistaken, for mode 5 and 6. But when we use the EVO, we are able to basically take into account that local deformation or that local mass concentration that we have from the tank as well, as it influences the overall market distribution. And then we also have other methods such as the pseudo orthogonality check, which we can also basically use as a metric to check. This is basically a faster method compared to the EVO, so it is computationally less expensive compared to the EVO method. And it also gives us a very good correlation, especially if identifying the local modes of the tank for modes 5 and 6 here. So that is also another option available within FEMtools that we can use to basically do our test correlation. That basically brings me to the end of the demo case here. So I would like to maybe switch back into the presentation as we have here. Go into presentation mode. No, so here. So going below, we've been able to basically compare our test model with our FE model, but looking at it, we are still not there. We see still there is more room for improvement, I would say. So that is something that we look forward to improving. So we've done the first step of correlation. So the next step now is to basically identify parameters inside our models that we can update to basically gain a better correlation because we see, for instance, in the mark plot that there is a lot of, if you go from mode to mode, there is high differences between the FE and the test mode. So the next step now is to basically be able to identify how we are able to use this to basically update and get a better correlation. And here as well, we also have the major differences, as I showed in the demo, between the MAC, the EVO, and the POC. So the POC is fast but approximation of the EVO, and here we can identify the two modes, the two local modes, or get a better correlation for the local modes of the tank as well. So to conclude, we have a variable differences in frequencies ranging from -15 to 30% from mode to mode. And the mark is also 90% or it's larger than 90% for the global modes, 1 and 2, and 50 to 60% for the local modes. So which means that global scaling of stiffness or mass is not sufficient to reduce the frequencies due to the variation that we get from mode to mode. And below here, we also have our test correlation quality criteria. So the main idea here is to get the fundamental bending modes. So we want the frequency differences to be below 33% and also with a mark greater than 90%. And also for modes with effective mass higher than 10%, we would like to have a frequency difference less than 5% and a mark greater than 85%. So the next step now, which I'm also happy to share, is our next webinar scheduled on 29th October on FE model updating and sensitivity, where we will basically take this a step forward and basically apply methods for finding and updating the parameters that can satisfy the target correlation levels as stated here in the quality criteria. So if everything I've described today sounds like music to the ear, then we welcome you to our next webinar. We'll be sending out invitation soon. So everyone present today will receive an invitation to sign up on 29th October, where we will look at model updating, and it's also scheduled at 4 p.m. Yeah, feel free to join. And if there are any questions or whatsoever, please feel free to let us know.
Kelvin, with referring to your conclusions slide, I think during the demo you did not really highlight the mode shape pair table. So because here you mentioned a range from -15 to 30, but I think this table came up in the console, but maybe you can highlight that again in the correlation table.
Yeah. So we have it here for the model assurance criteria.
Yeah, but it is the mode shape pairing table that we see currently in the console, but it's also there in the mode shape pairs.
Oh yeah, there it is. Yeah. Thanks, Eddie. So yeah, I think I skipped that for a bit. So here we definitely see the differences that I described in the conclusion here. So here it's actually very clear to see side by side the differences between each of the modes, each of the mode pairs for the FE and the experimental modes here. So as you can see, as we go from mode to mode, we see differences, which means that in this case, we will have to find a way, typically a local method of updating our model to basically get a better correlation here. So this is just to show the differences as we've seen from the conclusion between each of as we go from each mode to each mode. So thanks, Eddie, for pointing that out. Yeah.
Yeah. So here you can also see that the MAC for modes pair 4 and 5 is is lower than for the global modes. So these are the local modes for the tank. And yeah, so with the orthogonality check, we could bring those percentages much higher, which so this mode shape pair really sticks out better than with MAC. And this can be important when in next phases we will do automated mode pairing as part of an updating loop, so that the better the initial correlation can be identified, the safer it is that during the updating we will be able to make that automated pairing work. And because we sometimes have the question about to clarify the difference between MAC and orthogonality, and I check, and I think Kelvin briefly mentioned it, is that for the computation of MAC, every degree of freedom, every measurement actually is treated in an equal way. It has the same weight. It's basically a vector correlation criteria, MAC, whereas the orthogonality check is in fact computing modal masses. It's phi and phi, where phi is the mode shape. So it is weighted by the mass. So that's why with lump masses, you will typically see that the orthogonality check will result with different look at correlation, because no longer every degree of freedom has the same importance, but it's the ones where mass is concentrated, they actually get a higher weight, and so that can sometimes improve the capability to do mode shape correlation by favoring those locations where mass is concentrated.
Yeah.
Another question that I've seen coming in is that about how the interfacing with Nastran is done. So in FEMtools, we will be able to bring in the FE input deck, a bulk data file, as Kelvin did in this case, and also results through the OP2 file, output2 file. So that's Nastran terminology for the binary results files. These OP2 files are automatically created if you add output param post -5 in your Nastran bulk data. So -5 is a code that's specific for FEMtools, which will instruct Nastran to produce the necessary output2 files. And in the general case, this is there's actually 3 files that we need. One is with the mode shapes. This is in this version, it has the extension 51. This was the 4.51 file that Kelvin imported. And then we have one with the element stiffness matrices, .91, and one with the element mass matrices, .92. So these 3 files, if you don't use the param post -5, then you will instruct Nastran to produce them using alters. But by using that param post -5, it's fairly easy to get those files. And yeah, then we have a direct interface with those files to import them in FEMtools, so that modes and element matrices are becoming directly accessible. The element matrices are used, in this case, they were used for the effective mass computation. In next webinar, we will see that they are also important information when it comes to sensitivity analysis and updating of the finite element model. But that's for the next webinar.
Yeah.
I don't see any other questions coming in. I don't know from your side, Kelvin or Naima, if you have other things that need.
There is a question just now from Salvatore. Maybe you can have a look at the Q&A.
I didn't see that in the Q&A. Oh, okay, now it's okay. The maximum order selection is default, if you saw the MPE plot, so the question is how to determine what the maximum order should be in the modal extraction. And the estimation that FEMtools provide is based on a peak counting algorithm. So we check, or we estimate how many peaks there are in the frequency range of interest. And I think then ×3, but okay, that I'm not sure. So it is based on that estimated number of peaks. Then yeah, of course, the result will depend on the order you put there. But the higher you increase the order, the maximum order, the more potential you will see for matching peaks. Now, if you make it too high, then the algorithm will also start to try fitting noise peaks. So if you have significant noise in the data, that will be visible through small peaks in the curves. And yeah, with an increasing order, you provide actually the algorithm the possibility to fit also those small peaks, but they may not be physical poles but noise poles. So it's a matter of a trade-off between having enough. The order should be high enough to match, or yeah, so that every physical pole is included, but not too high to not include the noise poles. So yeah, that I think is there is no general rule there. It is largely depending on the quality of the data, and more specifically, yeah, how many peaks you can see, and also the presence of noise.
Yeah. Any other questions maybe present?
There is another question. I typically start out with 2 numbers of poles, +1, and then increase from there. It's I think it's an
so
answer.
okay, that's a remark from. So I think it's a bit by experience and from the quality of the data that you get, what is your starting point. But okay, as you see, it is very fast to extract these poles. So if you try with less or more, you can easily compare results with different settings. You can go to the next tab with the modes extraction. You can then look at the validation of the results. So you may then conclude that you are missing some poles. So you can come back to the previous tab, increase the order. So it is, as it is all almost interactive. It's very easy to try different settings. And yeah, I'm sure given the typical data that you are working with, you will develop some routine or some experience of what works best for your data.
Yeah.
I think those were all the questions we have at the moment.
Okay.
I think we are right on time. Might be a first, but glad to see that. So with that, I would like to thank every one of you for joining today for our talk. And just to remind you, we have a second part of this webinar, of the second part of this story, scheduled on 29th October, where we are going to do the model updating of the FE model to get better correlation. So we will be very glad to have you there available. So we will make announcements very soon on where to sign up and all this kind of stuff. So I would like to close here. Any remarks from you, Eddie, or from you, Naima?
No, thanks, Kelvin, for the excellent presentation.
No, thank you very much.
Yes, and thank you all for joining.
Yeah,
all right,
bye for now.
See you. Bye.